First of all, I'd like to thank the organizer to give.
Microphone.
Yeah, it's on.
Maybe closer.
Oh, maybe closer. It's better. Okay, thank you. First, I'd like to thank the organizer to give us opportunity to present our recent work on the ultra-thin tin telluride. So we find that there's ferroelectricity. The story that we want to study this material because this topological crystalline insulator. So, but unfortunately, we go to the another directions to find some ferroelectricity. But we find it's very interesting. So, my name is Shuaihua Ji from the Tsinghua University. So first, I'd like to acknowledge all the collaborators. So the work is mostly done by the Kai Chang, previous our students, and we collaborate with Professor Xue, Professor Chen, and Duan in our university. And Professor Zhang from Renmin University give us Raman's measurement. Professor Fu from the MIT, actually, he proposed this topological crystalline insulator a few years ago.
They can't hear from the back.
Oh.
Try to be even closer.
Even closer.
Yes.
Maybe a little bit louder.
Yes, and speak a bit louder.
Putting it on the other side.
Maybe, yeah. That's a good
To the right.
But there is a there is a challenge.
Maybe I can hold that
No, don't worry.
phone.
Talk now, louder.
Yeah, okay. I will speak a little bit louder. And also we collaborate with Professor Baraza Lobzi from University of Kansas. And we also have a collaboration with Professor Parkin in Max Planck Institute. So here's the outline of my talk. So I just give a very short introduction about the two-dimensional system, and then I will discuss about the ultra-thin tin telluride, and we find the ferroelectricity. And recently we also find that very interesting domain confined standing wave in this material. So two-dimensional systems has been widely exploited, and this technique I think everyone here is very familiar. So if you have a layered material and you got Scotch tape, and actually you can got a lot of very interesting two-dimensional systems. And I think the professor again always encourage his students to do some crazy Friday experiment. I think that this is some of this result. A lot of exciting experiment has been done in these directions. I just give some short, very brief introduction. So the graphene is very special because there's a linear dispersion around the Fermi level. So direct fermions is very special. Another very interesting you can see is the BKT transition. Although it's already has been discovered a long time ago, but recently people more focused on the layered material. These also are very old stories, but they give a different name. This is called the 2D topological state now. So, but this is a quantum Hall effect, but it's also can be understood in terms of the 2D topological state. If you introduce the electron-electron interaction, actually you could go to the fractal quantum Hall effect region. I think the ordered state is also very interesting for the people, such as the magnetic order system. So you can epitaxial growth some palladium ion bilayers on the iridium 1,1 surface. So this is you can see a lot of very interesting phases in this system. As you reduce this, you reduce your thickness, you always find that the transition temperature of the magnetic order will reduced. And normally in these ion films, they find the critical behavior near the TC is also very interesting. They find the beta is equal to 0.2. Which is larger than the 2D Ising model. That means your not only neighboring interaction is important, but also long-range interaction is also important. So how about the ferroelectricity thin films? People has been explored actually for a long time. So first in 1998, I think people already started the 2-unit cell polymers. They also find in the just 2-unit cell polymers, you also can see the heterogeneous loop. So that means you can get, and they find that the transition temperature is not dependent on the thickness. So they claim that this is ideal 2-dimensional system. I think PDTO is more familiar with our audience here, and people find that down to the 3-unit cell thickness, you can find some ferroelectricity in these thin films. And normally, when you reduce your thickness, in some regions, your TC can be enhanced compared to the bulk. But if you go to the limit, normally due to the reconstructions and this transition temperature will always go to 0 or very low. Normally they call it the dead layer. So it seems that if you want to go to the limit, you really have to control the interface, and you get very high quality thin films. Because I'm an STM guy, because I'm working on STM for a long time, so I think I like to give a short introduction about the STM. STM is you using a metal tip, so approaching a surface, and you go to the tunnel region. And if you keep the constant current, and you can get the topograph of the surface. Another very important technique is scanning tunneling spectroscopy. Actually, it can mirror the density state around the Fermi level. So this is very important information for a lot of materials. We can mirror using the lock-link technique, you can mirror the DIDV, that is a differential conductance. This is directly related to the density state of your sample, if you assume that your tip density state is featureless. Another important feature of STM, you can scan the surface in the nanometer scale. So you can do your DIDV in each point, and you can get a mapping. So here I give a example. This topological insulator surface, you can do this technique at different energy. You can see the surface density wave has a different wave length. So this technique actually is very important to get the electronic informations. So now I go to the second part is our ultra-thin tin telluride. So actually, the tin telluride actually is a very old story. So it's used to be called a ferroelectric semiconductor. It has been long time ago. But after a while, people shifted to the oxide. So all the studies have shifted to the oxide. So this material almost has been forgotten. And recently, people also have some interest on that because of the topological crystalline insulator property. These materials have the rock salt structure. And at a low temperature, it has a transition from the cubic to the rhombohedral structure transition. So the polarization is along the 1-1 directions. And in the history, the highest transition temperature you can get is only 100 Kelvin. This material has a serious problem of the tin vacancy. And you can see here the best sample you can get is around transition temperature 100 Kelvin. So in our experiment, we have put this limit up to the room temperature in the very thin film. It's really a surprise to us. So how we get the very good thin films? So actually, I think substrate choosing is very critical. We choose graphene terminated silicon carbide substrate. We also try grow these thin films on the silicon surface, but we find that the interface is hard to control. But if you change it to some inert surface like graphene, actually you can get very good thin film. And nearly people, it's not epitaxial because they don't have epitaxial relationship, but people always call it van der Waals epitaxial growth. So let's see how the film looks like. So you can this is the STM image. You can see the atomic steps on the sample. So this is graphene region. But you can see after deposition thin films, and you can see some rectangle island. The thickness is very small. It's just several unit cell. Just one unit cell is only 0.6 nanometers. So we always get 1 unit cell, 2 unit cell, 3 unit cell. And if you zoom in this island, you can see perfect square lattice here. It's almost no defect, almost no defect. And this is 001 surface of the tin telluride. And occasionally, we started this island. This island is 100 nanometer size. But during the scanning, there's some interactions between tip and the island, and you can see the whole island and sliding on the graphene surface. So that means if you give a very small force, actually the island can move. That means the interactions between our film and the substrate is quite slow, quite lower. So it's nearly a freestanding one. Why it is have a double atomic layer growth mode? So that means we using the DFT calculation shows that even numbers of the even number of atomic layers has a much lower surface formation energy. So you can see here all these even number layers have the lower energies. So at a very thin film thickness region, we always has the 2 layers growth mode. So that's why we got the 1 unit cell, 2 unit cell, 3 unit cell, like that. But if you increase the thickness, the energy difference becomes smaller, and then you can get the odd and even numbers, both of them. So now let's focus on just one layer thickness, just 1 unit cell thickness. That is only 0.63 nanometers. So that is what we got. So from the STM images, we can see directly on the thin films there's stripe structures. So that reminds us maybe that is the domain structures. And if you're looking carefully, you can see at the edges of this island, the color also different. If we do the DIDV measurement at the 3 point, A, B, C, 3 different points, we can see the gap edges actually will move. At the A point, it's around 1.5 volt. But for the B side, it's just a 1 volt. Inside of the island, the edges actually is in the middle. So why is that? So, and we also can measure the spatial resolved DIDV spectroscopy. So you can see the gap edges for the A point along these lines. You can see will have the bending here, right? And for the B side actually is a bending up, and this is quite natural actually for us, because at the edge of these thin films, the polarization is discontinuity. So that means there's a polarizing charge. This polarizing charge will give this bending effect. But however, we don't we know the bending directions, but we don't know what is the polarization directions. So this is actually a little bit challenging for us. actually, we can using the STM technique to get the very high resolution STM images. So you can see the tellurium atoms on the surface, and we can do the Fourier transfer. You can get the, I think this is from these spots we can get the lattice constant. What is surprising to us, we measure the lattice constant for each domains, and we find this oscillation relationship. For example, in the domain 1, you can see the lattice B is lattice constant B is larger than A, but for the number 2, it's reversed. And why is that? So it is well known that for the ferroelectricity materials, along the polarization directions, the lattice constant will be stressed. So that means in the domain, in the number 1 domains, along the B directions actually is the polarization direction. So, but we don't know which one because there's 2 directions. Combined with the H informations of the charge, so we can identify the in-plane polarization of these thin films. So actually, it's a little bit challenging, but we're very lucky to get this information. So you can see here all the polarization direction is head to tail to reduce the energy. Not only the straight line domain walls, but we also can see some zigzag structures domain wall. That means you have head-to-head structures here. This is very common. And sometimes, occasionally, you can see maybe 180-degree domain walls. And sometimes you can see the needle-like domain walls. So another evidence of the ferroelectricity is that you need to switch this polarization direction under the electric field. So fortunately, we have the electron. We have the tip can apply the bias. So under the bias of the STM tip, so we can see all the domains domain walls can move. You can see here the needle domains has completely disappeared. So that means in this region, the polarization directions actually can be switched. So this is also very critical evidence for the ferroelectricity. So now we can see, we can image in domains. We can see the bending by the polarization charge. We can see the lattice distortion and the domain walls movement under the electric field. So all this evidence support us that even down to the 1 unit cell thickness of the tin telluride, it still has ferroelectricity. So how about the transition temperature? Actually, I think it's very challenging because our sample only nanometer size. So the scale is 100 nanometer size. And if you want to measure it, the transition temperature is quite challenging. And our students find a very good way to do it. That is a variable temperature STM measurement. That is a much challenger to me. So, because if you want to measure the lattice constant at different energy, you have to, at different temperature, you have to calibrate your lattice constants, you calibrate your STM at a different temperature. So that is impossible. We can find another way. We're using the distortion angle between the distortion angle to characterize this polarization. So if you do the measurement of the STM and very high resolution STM images, and then you can do the Fourier transfer, actually we can see that the Bragg peaks, there's 2 sets of Bragg peak, not only 1. So why there's 2 sets? Because for the 2 domains, they have slightly lattice constant difference. So for the left side, you can see there's 1 set. For the right side, there's another set. So that's why you have 2 sets of Bragg peaks here, although it's very, very, very tiny, small. So from here, well, actually, we can using the domain wall as a reference. So, and then you can using the distortion angle delta alpha to characterize your polarization. If you have a distortion angle, and then you have a polarization. So that's the way how we characterize the ferroelectricity under different temperature. So you can. This is a real space, I think, the lattice constant vector, and you can transfer it to repeticle space. And the angles between these two vectors is delta alpha, is what we defined here. And then you and then from the Fourier transfer images, we can easily calculate our delta alpha at a different temperature, because this is just a relative, both has, I think, the length scale, so they cancel each other. So we don't have to calibrate our STM at different temperatures. So this is quite easy for us. So, and then we do the experiment at a different temperature. It's still challenging because of the drifting. So you have to find the exactly same regions and to monitor it at a different temperature. You go to the around the room temperature. It's still very challenging. And so you can see here, this is at the 84 Kelvin. So there's a splitting here. That means you still have distortions here. That means you still have polarization. As we increase the temperature, the splitting becomes smaller and smaller. Goes to when it goes to the 270 Kelvin, it's disappeared, almost disappeared. So we put all the variable temperature experiment data here. So you can see this is delta alpha versus temperature. You can see the delta alpha will continuously decrease to 0, and it goes around the 270, it goes to 0. So more surprisingly, that for the 2 and 4 unit cell tin telluride, we find that even at the room temperature, we still have these polarizations. So this is very exciting for us, because if you, at the room temperature, you have polarization, that means you probably you can have some applications. And we carefully started these transition behaviors around the TC. And we measure the delta alpha, because the delta alpha proportional to the P square of the P polarization. And the P has a relationship with temperature. So that's how determine the critical component beta. This beta is quite close to the 0.33. So this means that the long-range dipole interaction also important for this low-dimensional ferroelectric materials. And we also give other evidence, such as Raman shift measurement. For the thick films, we grow the 220 nanometers, so it's very thick. And we can monitor the TO mode. We can see that we can, using the square of the Raman shift, to extract it the transition temperature. This is around 100 Kelvin. So that means in the thicker films, it's quite close to the bulk material. But for the very thin films, you can see here, the peaks here is almost no changes, even go to the 100 Kelvin. So that means you still have polarizations even under the room temperature. This is another evidence. So why is enhancement? So let's see our thin film qualities. You can see here. So this is a 12.5 unit cell. You can see a lot of tin vacancies here. But for the unit cell, you almost see no defect at all. So, why is that? So we using the first principle to do the calculations. We find that when you reduce the thickness, your gap will enlarge due to the quantum confinement. And also we find that the formation energy of the tin vacancy will increase. So that's why when you reduce your thickness, the vacancy density will reduce almost by more than orders, one orders. So that's why I think there's a carrier screening effect is very important. So if you have a lot of vacancies, and then your TCs will dramatically dropped. So this is already very well known. Another important factors, I think, in the ultra-thin film, because of lattice relaxation, so implant lattice maybe will expansion. So that's maybe also another reason to enhance this ferroelectricity. Recently, there's several group interested in our work, and they find that maybe this enhancement there has some intrinsic origins. So this is also very interesting, but we need some experiment to prove that. And recently, I think this Van der Waals type of ferroelectricity material is also interesting. So let's give us a short summary. We have find very high quality telluride thin films. We find that there's a very large enhanced transition temperature. The second part, actually, I will go through very quickly. We find that very interesting, the domain wall of this system can confine electrons. So standing wave to everyone is very familiar. So here's a typical example. Your impurity on the copper 1,1 surface can form the standing waves. And here is quantum corrode. So normally you can see the standing wave at the edges because there's potential barriers. So if you incoming wave and scattering wave will have interference, you can have interference patterns. So how about the domain walls? We always find that the dark lines around the domain wall. So why is that? And we do the DIDV spectroscopy around the domain wall. Along these lines, we find that actually there's standing wave patterns here. So this is typically the particle in the box problems you can see. So you can see here there's 1 node, 2 node, 3 node, and around the domain walls actually there's no exit of the electron density state. So that's why you can see here it's dark. So reflection is very high. And our collaborators give us AB initial calculation support. He finds that around the domain wall there's no very high potential barriers. But why there's such kind of the electron confinement? So let's see the electronic structure. Along the gamma X directions, so we assume that the gamma X direction is the polarization direction. So here is a valence band. So if we see the electron structure at different energy, you can see at the beginning you have the pocket around the gamma X direction, and then you have the pocket around the gamma Y directions. So now we understand very well. Because of these domain structures, head to tail domain structures, there has 90-degree domain rotations. So if these domains, you have some band along the gamma K directions, in another domain actually it's rotated. So there's absence. So that's why you have very high confinement here. So we also started the energy dispersions. It's quite well with our theoretical calculations. So I don't have too much time to go through it. I will go very quickly. So this is just a modeling of Faraday parrot modeling. We can find that the reflection rate is very high, 0.7. And another evidence shows that very narrow domains also shows that there's no transmissions between the domain walls to these to near domains. Why is that? I think this tells us the domain confinement is very strong, and there's no transmissions there. But you previously tells us the reflection is 0.7. I think the scattering between the substrate is very strong. So at the end, I give a summary. So we find the very interesting atomic SiC tin telluride system have ferroelectricity and largely enhanced transition temperature. We also find some interesting domain work confined electronic state. It's maybe possible using in the future some devices. So it still have a lot of challenges. Can we get the tin telluride ferroelectric devices and the large-scale uniform thin films and the interplay between ferroelectricity and the strong spin-optical coupling is of our interesting problems. And at the end, thank you for your attention. Yeah.
Yes.
When you've shown your apparatus, I see 1 millikelvin and 15 Tesla, and then I don't see any magnetic field, and I see 100 Kelvin. So
yeah.
What's the relationship between that?
I think this is the first experiment run in our STM. So we didn't use it. But nowadays we are studying the superconductor.
You would like also to apply magnetic field, this is the
Yes. We studied the 2D superconductor.
So, and why have 1 millikelvin since what we need is 100?
Oh, 60 millikelvin. So we want to study the 2D superconductors. So usually the transition temperature is very low. So that's the reason. Yeah.
Hey, thank you. Very nice talk. Is there any chance that you're looking at ferroelasticity rather than ferroelectricity?
Pardon? Sorry.
So could these images correspond to ferroelastic distortion and ferroelastic order parameter rather than ferroelectric?
You mean just lattice distortion, right?
Right.
Yeah. Yes, I think the referee also asked the questions for me.
Okay, that was not the purpose. Because tin telluride is known to have a ferroelastic component, I believe.
Actually, we compared both of them because if we only consider the lattice distortion and we compare with also the ferroelectricity, we find for the ferroelectricity systems it has a much higher confinement effect. So, yeah.
Okay. One more quick question, but please start preparing the presentation.
Do you see any influence of your ferroelectric on the in-plane transport properties of graphene?
Yeah, it's a very good question. Actually, we are trying to do experiment on that. So we expect that there's some very strong effect on that. Yeah. Thank you.
So let's thank our speaker again.
Thank you.